All right, let's talk about how to calculate integrals on a calculator. Welcome back to my calculus videos. This is video 7 of the definite integral. And first of all, where do I find it on my Texas Instruments calculator? Math option 9 is the definite integral. um, and I'm going to show you how to do two different calculators, 83 and 84 of the TI line. And the first one is 83. But let's start by looking at our integral. We are finding the integral from a to b of some function with respect to x. So remember again, the integral from a to b of f of x with respect to x. And if you've got a TI-83, it's going to look something like this. And I'm going to be doing a little bit of back and forth cutting and pasting to show you what they look like. When you choose Math 9, you're going to see the function integration. You type your function in right here. You type your variable in right there. A and B. So this is f of x, comma, x, comma, A, comma, B. And for the purposes of using the TI, this will always be a function of x, and these two should always match. So that's your TI-83, and you can see that I did the area under the curve x squared from 0 to 3, so we're looking at this right here. We want to know this area right there. There's 3, and this is y equals x squared. That has an area of 9. All right, excuse me. So that is the TI-83 calculator. The TI-84 calculator has something called MathPrint. And MathPrint is just basically what it sounds like, which is, wow, isn't that beautiful? Looks exactly like you'd write it on paper. So there's our lower bound, there's our upper bound, there's our function, and there's our variable of integration. You can also, just so you know, if you've typed your equation into y1 or some register in your editor, you can always type y1 there or enter. You wouldn't type it, but you enter y1 there using your menus instead of having to retype the equation each time if you're doing a whole bunch of work. Okay, so there's that, and notice same one. Same integral, it's also equal to 9. Okay, so what about let's do a few examples, and why don't you go ahead and pause after we type in pause after I write each example, type it in your calculator, and then see if your answer matches. The integral from -1 to 2 of x sine of x dx is approximately, pause, back 2.043. Always going to go to 3 decimals in AP calculus. Whether you go to 3 or different in your calculus class will depend on yours, and in real life it'll depend on what you need. The integral from 0 to 1 of 4 over 1 plus x squared dx is approximately, pause, and we're back, 3.142. And the integral from 0 to 5 of e to the negative x squared dx is approximately, pause, and we're back, 0.886. You'll notice that these are not easy to do geometrically. The ones we had done up till now were all really simple geometrics to give you the idea of, hey, here's how we do it. And of course, you could also do for each of these a Riemann sum in the Riemann program on your calculator, and depending on how many partitions you put in, you would get closer and closer to these three numbers. All right, now let's talk about how we graph these functions. So I've got f of x, an accumulator function, which is the integral from 0 to x of 1 plus t cosine of t dt. Now, we need to notice a couple things here. First of all, you'll notice that this is 0 to x because you're going to sum, wow, well, that just completely obscured my letter, which I wasn't expecting. You're going from 0 to some place x. And because of that, we have to have a different variable here. So if I were to think of this as some function, blah, from 0 to t, and so my function is defined from here to here. My accumulator function, my integral, starts right here and goes to some value of x. And as long as x is between 0 and t, I can calculate that area. So this is why we have two different variables. T is the function, it's the black function drawn on there, and x is the amount that I want to know. So if I want to know how much snow has fallen by 2:30 in the morning, I set x to 2:30. The function for how much snow has fallen is the function of t. So let's take a look at this accumulator function, and then I will show you very quickly how to drop it into our calculator. So I've got a graph here, and the graph has both the original function, y equals 1 plus t cosine of t, and the accumulator function, which is the area under that curve. So pause for a second, look at that, and think, okay, which is which and how could I tell? And we're back. So let's think about this. If the area under the curve, if I go at x equals 0, that's this rectangle here. And the width of that rectangle is 0, which means that the area under the curve from 0 to 0 must be 0. We'll talk about that more later. But that means that the accumulator function f of x must be here, and that the function itself, whoops, went too far there. The function itself must be this. And it doesn't really matter if I have any idea how to calculate it or what it looks like. It doesn't really matter. The area right here has to be 0, so there's no question that this accumulator function must have started with an area of 0. All right, finally, let's take a look at how do I put this accumulator into my calculator. And I've got another quick graphic for you. Here we go. There it is. I'm just going to put my original function in as my first equation, y1 equals. Notice that I do have to change these to x, which means I'm awkwardly going to have x's everywhere, even though these technically should be f of, whoops, wow, that didn't write very well, f of t. I don't really have the option of putting a t in there. Don't be fooled by the fact that you could manually type in a t. Your equation editor in your graphing calculator will not recognize it and won't know what to do. So here's my original function. Here's my integral. Notice that I can just reference the first function, so I don't have to retype the whole thing again. And then when I hit graph, I will get the graph that I showed you previously. All right. So we'll be back with one more video for this chapter. We're going to talk a little bit about discontinuous functions and what does it look like when we do those integrals. Thanks for watching.